Digital Visual Interface, DVI. The Digital Visual Interface, or DVI, represents a critical transitional era in computer display technology. Developed by the Digital Display Working Group in the late 1990s, DVI was designed to replace the aging analog VGA standard. Its primary mission was to create a high-speed digital connection that could deliver uncompressed video data to modern flat-panel LCD monitors. Unlike VGA, which requires a double conversion, where the digital computer signal is converted to analog and then back to digital by the monitor, DVI allows the digital data to stay in its native format from the graphics card all the way to the screen. For a technician, DVI is one of the most complex connectors to understand because of its multiple variations, ranging from pure analog to high-bandwidth digital. The engineering of TMDS. To achieve its high speeds, DVI utilizes a technology called Transition Minimized Differential Signaling, or TMDS. This is the same underlying signaling method used by HDMI. By sending the data in a specific way that minimizes electrical transitions on the copper wires, DVI significantly reduces the amount of electromagnetic interference it produces. This allows for a very stable, high-resolution image even with longer cables. A unique feature of DVI is how it handles bandwidth through links. A standard DVI cable uses a single-link configuration, which employs 3 TMDS data channels. This provides enough bandwidth to support a resolution of 1920 by 1200 at 60 Hz. However, as monitors grew larger, the industry introduced dual-link DVI. By adding a second set of TMDS channels, dual-link effectively doubles the bandwidth, allowing for resolutions up to 2560 by 1600. As a technician, you can identify a dual-link cable by looking at the pins. A single-link plug has 2 distinct blocks of 9 pins with a gap in the middle, while a dual-link plug has a solid, continuous block of 24 pins. The 3 faces of DVI, D, A, and I. The most confusing aspect of DVI for many users and junior technicians is that the physical port can support 3 entirely different types of signals. You must look closely at the shape of the connector to know which one you are dealing with. DVI-D, digital-only. The DVI-D connector is designed strictly for digital signals. It is used to connect a digital graphics card to a digital LCD monitor. You can identify a DVI-D port by looking at the large flat pin on the side. In a DVI-D connector, this flat pin stands alone. Because it does not carry any analog information, you cannot use a simple, passive adapter to plug a VGA monitor into a DVI-D port. If you try to do so, the monitor will remain black because the digital signal is a completely different language than the analog VGA signal. DVI-A, analog only. The DVI-A connector is quite rare in the modern world. It was designed to carry only an analog signal, essentially acting as a VGA cable in a different shaped plug. It was used during the early days of the digital transition to allow people to use high-quality analog CRT monitors with newer DVI-style graphics cards. You can identify DVI-A by the 4 extra pins surrounding the large flat pin on the side. These 4 pins carry the red, green, blue, and horizontal sync information required for analog displays. DVI-I, integrated digital and analog. The DVI-I connector is the universal version of the port. It contains both the digital TMDS pins and the analog VGA pins in a single connector. This was extremely popular on graphics cards for over a decade because it gave the user total flexibility. You could plug in a modern digital monitor with a DVI-D cable, or you could use a cheap, $5 plastic adapter to plug in an old VGA monitor. The graphics card would sense which pins were being used and send the correct signal accordingly. Physical construction and security. DVI was designed for a time when computers were large, stationary machines kept under a desk. As such, the connector is quite large and rugged. It features a shielded twisted pair design inside the cable to protect the digital signal from the electrical noise. generated by the computer's power supply. One of the most notable physical features of the DVI connector is the use of dual thumb screws. Unlike the friction-fit design of HDMI or USB, a DVI cable is meant to be screwed into the back of the computer. This creates a very secure, semi-permanent connection that will not come loose if the computer is bumped or if cables are tugged. While this provides great stability, it can be a source of frustration for technicians working in cramped spaces behind a desk, as the screws can be difficult to turn by hand and often become stripped or stuck over time. The lack of audio and the HDMI connection. A critical technical limitation of DVI is that it was designed strictly as a Roman 6 DO interface. Unlike HDMI, the standard DVI specification does not carry an audio signal. If you connect a computer to a monitor using a DVI cable, you must run a separate 3.5mm audio cable if you want to use the monitor's built-in speakers. However, because DVI and HDMI use the exact same TMDS signaling for video, they are electrically compatible. This means you can buy a simple, inexpensive cable that has a DVI plug on one end and an HDMI plug on the other. This is a lifesaver for technicians who need to connect an older office desktop to a modern television or projector. In some rare cases, certain graphics card manufacturers cheated the DVI standard and allowed audio to pass through the DVI port specifically for these HDMI adapters. But this is not a guaranteed feature of the standard and should not be relied upon in a professional environment. Troubleshooting and the limits of DVI. When troubleshooting DVI connections, a technician must be aware of signal attenuation. Because DVI is a high-frequency digital signal, it is very sensitive to cable length. A standard DVI cable is generally limited to about 5 meters or 15 feet. Beyond this distance, you may begin to see digital artifacts on the screen, which often look like tiny flickering pixels or sparkles, especially in the dark areas of the image. For distances longer than 5 meters, a technician must use an active DVI booster or a specialized fiber optic DVI extension. Another common issue is pin damage. Because a dual-link DVI connector has 29 delicate pins, it is very easy for a user to accidentally bend one of the pins if they try to force the connector in upside down. A bent pin can result in a total loss of signal, or even worse, a missing color. If a monitor suddenly looks completely green or completely yellow, the first thing a technician should do is unplug the DVI cable and look for a bent or recessed pin in the connector.